We have a group of presenters today, but firstly, I have the pleasure to introduce our speaker today, John Dobkin. Promoting science and fact-based discussion about nuclear energy and spent nuclear fuel has been one of John's passion for decades. He has ample opportunities for national and community outreach. And one thing really interests me the most was that he also worked as a television news anchor and reporter for 14 years for various stations across the country. And I thought that was very impressive. And prior to joining SCE, John led external engagement strategies for Energy Northwest, owner and operator of Columbia Generating Station in Washington State. So welcome, John.
Thank you. Thank you very much. I appreciate the opportunity to be able to present to you about what's going on at San Onofre Nuclear Generating Station, or SONGS as we like to call it for short. We have a couple of members from the SONGS team here, and so I'd like to introduce them. Julie Holt, who is a former engineer, project manager at SONGS, and lives the closest to the plant of all of us. So it's interesting that SONGS is basically in her backyard. And then also a couple folks we work with, Melinda Andrade and Todd Priest. So I want to acknowledge them for being on the meeting as well. And I can't see if there's anybody else from the SONGS team on here. So with that, I guess, Julie, if we want to launch into the presentation, we can go ahead and do that. All right. So once again, thank you very much for the opportunity to present to you on the work that's taking place at San Onofre Nuclear Generating Station. We are now in decommissioning, which is very different from an operating nuclear plant. And so what I'm going to do through this presentation is talk a little bit about the dismantlement that is going on right now at SONGS, and then also sort of give you a kind of the longer term picture of what's going to be going on with the site in terms of management of spent nuclear fuel storage. So we'll start with a brief overview of the decommissioning and dismantlement, and then move on to the spent fuel. So in terms of decommissioning a nuclear plant, all nuclear plants go through decommissioning after they're retired. And so when we retired the plant in 2013, we went right into a decommissioning phase. And as part of that, we developed these goals and principles, our principles of safety, stewardship, and engagement. Safety is always the top priority and always very important for whether you're an operating nuclear plant or one that's in decommissioning. And we take that very seriously. Now, in decommissioning, most of the safety focus is of an industrial nature because we're deconstructing the plant. But there is still some radiological or elements of safety that remain important to us as we go through this decommissioning. In terms of stewardship, most of you know where San Onofre is located. It's in a beautiful location on the California coast. We're surrounded by state beaches to the north and south. So in terms of environmental stewardship, very important to us. But also there's an economic stewardship that is also important, and that has to do with our decommissioning trust fund, which we are managing so that we can complete the decommissioning utilizing those funds. And lastly, engagement. We really cherish opportunities like this to be able to speak to folks about what's happening at SONGS and be able to share what's going on there and let people know what our plans are, how the work is progressing, and how we're meeting our commitments to various federal and state agencies as we go through this process. So engagement is very important in that regard. In terms of the plant itself, there were 3 units built on the SONGS site, and the site itself is only about 85 acres, so it's not a large area. But Unit 1 went online back in the late 60s. It was retired in 1992, And units 2 and 3 were then developed and went online in the early 80s. And both of those were retired permanently. They were shut down in 2012 after we had an issue with our replacement steam generators, and then permanently retired in 2013. And really, since that time, we've been focused on decommissioning the site. And then we've had spent nuclear fuel in storage for over 50 years and in dry cask storage since 2003. So this is our decommissioning plan. Now, the question, obviously comes up, what is decommissioning? Well, decommissioning is a process that's governed by the Nuclear Regulatory Commission. And each nuclear plant, as I mentioned, after it's retired, will go into this decommissioning period. Now, the Nuclear Regulatory Commission gives plants 60 years to decommission. When we retired the plant in 2013, our decommissioning trust fund was of a significant amount where we could go ahead and begin the dismantlement work. The 60-year period is given to allow some plants that may not have a fully funded decommissioning trust fund to allow that fund to build up before they begin dismantlement of the plant. But because of where we're located on Camp Pendleton, we lease the land from the U.S. Navy, so they obviously would like it back for their mission at Camp Pendleton. So we went ahead and decided to go ahead and begin decommissioning. And so that's the process that we're in now. And really what it is those first two red lines there, dotted red lines, major decommissioning work, that's where we are right now. The long blue line, all fuel and dry storage, is there because there is no place to relocate our spent nuclear fuel to. The federal government was to begin in 1998 picking up spent nuclear fuel from sites across the country. They haven't done that yet. There is no national repository available to relocate the fuel to. So that means it will stay on site until we have that opportunity to relocate it. And so currently, our decommissioning plan takes it out to around 2050, 2051. But we hope, and I'll talk a little bit more about this later, to catalyze some action to get that moving sooner. So in terms of major decommissioning work, what does that look like? Well, we're really in year 2 now of dismantlement. We put out a notice of deconstruction early last year and worked through the initial round of COVID. We put COVID protocols in place so we could continue doing some of the work that we were doing, including completing fuel transfer operations, which was moving all of the spent fuel from pools into dry storage. And so we've been working on that. And just last month, we started building demolition. So if you see in that bottom right-hand photo, that's one of the K buildings, K60 warehouse building that really was the first to come down. And those K buildings were the first buildings built during the Unit 2 and 3 construction period. So that was where a lot of the engineers had their offices, and a lot of the meetings took place as Units 2 and 3 were being constructed. So in the upper right, that's the Unit 2 containment opening. So what we're doing is widening those openings to be able to get equipment into the containment domes to be able to work on all the equipment that's in there, because that has to be removed before we can bring the domes down. So this is a timeline of some of the major work streams that are going to be going on during decommissioning. You can see down, containment preparation and internal component removal will be taking place over the next several years. There is a lot of material in the domes that will need to come out before we can actually demolish those. And there's a lot of other buildings and structures on site that will all need to go. In terms of building a nuclear power plant, they take a long time to build because they are very robust structures. You can see from this photo the amount of material that just goes into constructing a containment dome. So you have, this is sort of the inner rebar and other what are called tendons that help strengthen the dome when it's built, but the walls are 4 feet thick. And there's I believe a 1-inch steel liner on the inside of the containment dome. So, they're meant to contain anything in the event of an accident. And so they are very strong. And it will be interesting when we do take those down. The way they will do it is they will weaken, let's say, the bottom 6 feet of the structure, and then it will collapse down. They'll remove that debris, weaken another 6 feet of the structure, and it'll just keep collapsing down until it disappears and all of that material is removed. So I mentioned inside the containment dome, there's a lot of material. And there really is, there's not a lot of, even the top of the containment dome has a large crane that circles the entire structure. So really, there's not a lot of empty space inside the containment domes, and all this material will need to be removed, including the reactors themselves. So that's the work that's beginning right now. We made those containment hatch openings so we can get equipment in that will help us then disassemble the reactors, and those will be done using specialized tools that can cut up the different segments of the reactor underwater for radiation shielding. And then all of that material will be removed. And depending on the level of radioactivity to it, it'll either be stored on site or shipped off site. So as I mentioned, lots of stuff. Lots of stuff. This is the photo on the right is the turbine building where basically the electricity was generated, and the photo on the left is inside the turbine building. And again, these structures are very robust in terms of the amount of steel and concrete that are used to construct them. And so in all, about 2 billion pounds of material will be leaving the site during this dismantlement phase. And the material is destined for landfills outside of California. So none of the landfill or scrap material will be staying in the state. It will all be going either to Utah, Arizona, or West Texas. So the low-level radiological waste will be going to facilities in Utah and Texas. And then, as I mentioned, the higher level waste, which is known as greater than Class C waste, we will put those into storage canisters and keep those on site until a permanent repository is available, and then those will be shipped off as well. And most of the waste is going to be going by rail. So we will have about 5,000 rail cars, like you see in that photo with the blue car with the white top to it, that will be leaving the site over the next 8 years. And rail is much more efficient than truck. You can put about 6 truckloads worth of material in one rail car. So it's much more environmentally friendly to go rail versus truck. And it also reduces any traffic congestion. So currently we have this one rail line going into the site, but if you look at the office building that's behind the train engine there, that's actually where Julie and I used to have our offices. We've been relocated to another section of the plant because that building is going to be torn down over the next several months. And once it's gone, a mini rail yard will be created in that space. And so we'll have much more opportunity to get more rail cars in there and be able to load up the material and ship it off site. When all is said and done, about 2029, this is sort of what the site will look like. The switchyard will remain. You're probably familiar if you've driven down Interstate 5 and you see the power lines that are going over the interstate. That's a main connection between San Diego Gas and Electric to the south and Southern California Edison to the north. So that switchyard will remain. The independent spent fuel storage installation, which is what we call our dry fuel storage facilities, that will remain until we have a place to relocate the fuel to. And then the seawall, the walkway, and the riprap that front the plant will also remain. A lot of folks don't know there is a public walkway in front of the plant that you can go from San Onofre State Beach to the north to the south side on that walkway. So that will remain until we can relocate the fuel, and then those elements will probably be gone. The switchyard will probably remain, but the other elements will be gone, and then we'll work with the Navy on final site disposition before turning it back over to them. And so if you're standing on San Onofre State Beach to the south and you're looking north about 2029, your view will be drastically different. The domes and other things will be gone, and just the seawall will be remaining. So that's sort of the end state of where we're going with the decommissioning and the dismantlement of San Onofre Nuclear Generating Station. So, so if you have any questions about the dismantlement process, we're going to take those at the end. But I want to talk a little bit about how we manage spent nuclear fuel on site, because that is a topic that certainly gets a lot of attention, and it's worth talking about. So, as I mentioned, we are storing spent fuel at Songs because there is no national repository where this fuel can go. In 1982, the Nuclear Waste Policy Act was created, and in that act, we were going to create a national repository that was created at Yucca Mountain in Nevada. And by 1998, the Department of Energy was to come to local nuclear sites across the country and begin picking up spent nuclear fuel. Well, that didn't happen. Here we are in 2021, and there is no national repository in sight. And so nuclear plants across the country created these independent spent fuel storage installations, or ISFSIs, dry fuel storage systems that can store the fuel until a repository is licensed and constructed and can begin accepting fuel. So this really began in 1986 with the first dry fuel storage systems being developed, and then it really took off during the late 1990s and early 2000s. As I mentioned, we started storing fuel in 2003. First, you always store spent nuclear fuel in large pools of water for about 5 years. And then you can take the fuel out and put it in a dry cask or canister storage. And so that's what nuclear plants did. And so we had fuel that was in large pools. We've gotten all that fuel out of the pools and into dry storage, where arguably it's a much safer environment for spent nuclear fuel. So in this photo here, I am sitting about 6 feet above 20 tons of spent nuclear fuel. This is our Holtec system. And in the Holtec system, we have 73 canisters of spent nuclear fuel. And the systems themselves are very passive. So they don't require electricity. They don't require any water. The canisters themselves are inerted with helium. There's no water inside. And so you can see that vent next to my leg there. The air goes in that vent and then comes out the little chimney stack behind me, much warmer than when it went in. So, you can have ambient air go in at 70 degrees, and it'll come out about 120 or so degrees. And it's basically all it's doing is taking the heat from the canister and convection cooling and allowing the canisters to remain cool. So, but in this photo, I'm not wearing any radiation dosimetry to measure my dose. I don't need any protective clothing. I don't need anything like that, because the shielding of the system is so great that the dose I would be getting from sitting on this canister is negligible. I'd probably get as much dose from being in the sun as I would from the spent nuclear fuel. So that's very important when we talk about how we safely store spent nuclear fuel, is the shielding of the systems, and the shielding here is very good. So what is spent nuclear fuel? Well, it's a solid. The canisters don't leak. It's not like on The Simpsons. If you watch The Simpsons, it's not green goo or anything like that. Spent nuclear fuel really is just a solid pellet. And you can see one of those little pellets there. They're about the size of a pencil eraser. And you put thousands of those into a fuel assembly. That fuel assembly there is just a demonstration one. An actual fuel assembly is about 15 feet tall, so probably 2 or 3 times the size of that. And in the Holtec system, we can put 37 fuel assemblies into one canister. Now, the fuel itself undergoes a bit of a change. So when we put fuel into the reactor, it's 95% uranium-238, which is just natural uranium that you can find, in the ground anywhere. And then 5% of it is uranium-235, which is the fissionable isotope of uranium. And what that means is that if you hit a uranium-235 atom with a neutron, it will split apart and create heat, and then it will also release more neutrons that will then go out and split other uranium-235 atoms. And so you get that chain reaction going. And really what you're doing is you're just creating heat to boil water to create steam, which turns a turbine, which creates electricity. So after 6 years in the reactor, the fuel does undergo a change. So we still have 95% of uranium-238, but now we're only down to 1% of uranium-235 and 1% plutonium, which we created during the fission process, and then also fission that as well to some extent to create heat. And then we have 3% of what are called fission products. Now, these are other elements that are more radioactive. They have shorter half-lives, probably on the order of 30-year half-lives, which means they're a little more highly radioactive than, let's say, plutonium or uranium. And so those are the ones that you really have to, why you're really shielding this fuel from employees and the public and the environment. So, but after 300 years, those will be gone as well, because basically what a half-life means is in 30 years, you have half of what you started with. So if you can kind of picture every 30 years, you're going half, 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 half until you have nothing. So that's what that is going through. But, you have, various other, if we can go back to that slide, that one, Julie. So if you are looking at those types of things, you've got, obviously plutonium has a very long half-life, 24,000 years or so. So, but really what that means is it's not very radioactive. So it's not really giving off a lot of radiation as long as you keep it on the outside of your body. So it's a very weak alpha radiation emitter. So you can, I could have some plutonium sitting here on the desk next to me and not be affected by it. But if you ingest it, then it's a different story, and then it becomes a health hazard. So that gets more into radiation science, and don't want to really get too deep into that. But it's an important concept because there are different types of radiation that we account for on site, and that's something that goes into our priority when it comes to safety. So with all that, what we're seeing in the community is really a disconnect between some and really the sort of the science and fact-based nature of spent nuclear fuel. So this chart kind of sums it up in terms of the risks at San Onofre continue to go down, while the rhetoric about spent nuclear fuel and what it is seems to be going up. And we're doing what we can in terms of the information that we put on our website to really try and help people understand what spent nuclear fuel is and what it isn't. So, you will hear some people say that, spent nuclear fuel can affect 8.4 billion people within 50 miles. And it's really just not the case. You can't, the physics just aren't there to have something like that happen. This is not an operating reactor like Fukushima, which has, tremendous heat and water and all this, pressures and things like that going on. As I mentioned, spent nuclear fuel is in a sealed canister. There's no water in the canister. It's inerted with helium, which is an inert gas. And it basically will just sit there, and there's nothing to spark anything. You could have some people talk about a crack in the canister, but really, if there were a crack in a canister, nothing would basically happen that would affect anybody outside of that immediate area where the canister is. You would perhaps release some radioactive gas that would dissipate very quickly, xenon gas, for instance. And then you would go ahead and initiate a repair on a canister. But the canisters that we have in use are extremely robust. And I want to talk a little bit about that in a second. But really, so what we're trying to do here is really help educate folks on spent nuclear fuel and try and give people the facts about what it is and what it isn't. It's not Chernobyl in a can. And I'll go through some of the other things that we did with our canisters to make them even safer. So we'll talk a little bit more about that in a second. As I mentioned, we have two dry fuel storage systems on site. We have the Holtec system, which we just finished loading in August of last year with 73 spent fuel canisters. And then we have the Areva system, which we started loading in 2003, and that has 50 spent fuel canisters. So two different systems, but still extremely robust in terms of how they protect the spent nuclear fuel and how they protect people and the environment. So if you've never seen a canister of spent nuclear fuel, this next slide we're going to show you what that looks like. This is just a test canister that we have on site. So in terms of monitoring our canisters for corrosion and those types of things, we developed this test canister, which is electrically heated, and it sits in the Holtec storage system. So, but it doesn't have any nuclear material in it. So we can remove it and look at it anytime we want to see if there are any corrosion processes at work with it. But these canisters are extremely robust. When filled, they weigh about 50 tons. Our canisters are made of 5/8 inch stainless steel. Most canisters in the US are about a 1/2 inch. We use 316L stainless steel because it's more highly corrosion resistant. A lot of canisters are made of 304 stainless steel. The welds in the canisters we had are laser peen. So the limiting factor for stainless steel canister is something called chloride-induced stress corrosion cracking. And what that is, the salts in the air would deposit on the canister and begin to cause some pitting and some other corrosion effects. Well, that really only happens around what are called heat affected zones where the welds are. So by laser peening the welds, we put a layer of compressive stress on the welds that essentially eliminates the potential for chloride-induced stress corrosion cracking. So in terms of the service life of these canisters, they can be used for 100 years or more. And then, we do get a lot of questions about earthquakes and tsunamis and things like that. The seismic rating is 1.5 G for these storage systems. The plants, when they were operating, were 0.67 G, and that's movement in a horizontal motion, shaking that you would get during an earthquake. So they're more than twice what the plant was rated at. And if you go back and look at Fukushima, which had a 9.0 earthquake, the shaking there was 0.561 G. So these are nearly 3 times the rating of what the shaking was at Fukushima. In terms of tsunami, the largest postulated tsunami that could happen at the site is 3 meters, which is less than 10 feet. But these canisters, the Arriva system, can be inundated by 50 feet of water, the Holtec system by 125 feet of water, and still perform their safety functions. So very well designed in terms of that. I mentioned the service life of 100 years or more, and more than 93% of the spent nuclear fuel storage systems in the United States utilize this type of technology, welded lid, stainless steel canisters. And so you might hear a lot of some other folks who are advocating for these thick-walled casks that they use in Europe. Those casks aren't licensed for transportation here in the United States. Thick-walled casks are more for a country that is going to recycle its fuel. So you want to be able to open it up. They have bolted lids on them, so you can open them up and remove the fuel and reprocess it if you want. We don't have a reprocessing program here in the United States. So our canisters are welded closed and they're leak tested before put into storage. And so you don't want to open them back up, and there really is no need to open them back up. The fuel will just sit there and undergo radioactive decay. So this is an important slide because it shows that if we had some place to move our spent fuel to, more than 80% of our canisters would be eligible to be transported today. But as I mentioned, we don't have a place to relocate the fuel to. But the good news is by 2030, all of our canisters will be able to be transported when a national repository or federal interim storage site is available. And that's very important to us. We wanted to make sure that when we looked for a canister system, it had NRC approval for both storage and transportation. Those thick-walled casks that people talk about do not have NRC approval for transportation. So they would be basically stranded on site, which is another important concept. So next steps, where are we going to go? Well, in terms of spent fuel storage, last month we released a 3-volume set of plans that really chart a pathway to try and restart the federal government and others into really looking at this issue of long-term deep geologic storage of spent nuclear fuel. I mentioned 1998 was when fuel was supposed to begin to be picked up from nuclear plants. We're more than 20 years on from that. Nothing has been happening. Yucca Mountain was basically mothballed for the most part 10 years ago. And so there's been actions here and there in regards to sort of restarting and looking at this process. And so we hope that these plans, we put together an action plan, which sets out some items that Southern California Edison can do now to be ready for when a repository opens. So we, are not, caught flat-footed where a repository is open and we haven't done the paperwork, everything else that needs to be done in order to be able to start moving the fuel. So we have that action plan. We have a strategic plan that really calls on a number of things you see here, which is advocacy, first of all, for federal legislation and appropriations to really restart this spent nuclear fuel storage program at the federal level, begin a national consolidated interim storage program so that, we could move the fuel to that site before a permanent national repository is built, so that we obviously get the fuel off of songs. We can turn the land back over to the Navy and they can use it for their mission with the Marine Corps. And then really, a conceptual transportation plan we put together that looks at how this fuel would be transported, what sorts of things would be required for that. And then as part of all this, we also, with our partners, launched a coalition. And the coalition is important because we really need to keep the energy up. Spent nuclear fuel, as I said, is stored safely. We're not doing this because it's dangerous or there's some, time frame that it needs to. As I mentioned, the canisters are good for 100 years, but that is not what Southern California Edison wants. It's not what nuclear plant owners across the country want. You've got spent nuclear fuel stranded at decommissioned sites across the country, including California. And so removing that from all these disparate places and putting it in one location and then finally a permanent geologic storage is the best route. And really, the federal government is in partial breach of the contract of that they signed with all nuclear plant owners back in 1982. And so we need to get some, catalyze some action. And that's really what this Coalition Action for Spent Fuel Solutions now is all about. And it's an opportunity for those in the community who don't think San Onofre is the right place for long-term storage of spent nuclear fuel, like we don't, to have their voices be heard. Sign up, join the coalition. We'll continue to give you information about what's happening, keep you up to date on the type of legislative action that's going on. Representative Mike Levin has been very involved from the get-go in terms of trying to get legislation passed and money appropriated to start, really kickstart this process. And but really, there needs to be a groundswell of support in order to make this happen. And so, if you agree that, again, San Onofre is not a good place or the best place to store spent nuclear fuel, then this coalition definitely would be something for you. And we encourage you to sign up for it. And again, it's very important that your voice can be heard, because like other complex policy issues, Southern California Edison can't do this alone. We definitely need help from the community, and we're very happy to see the support that we've gotten so far with the coalition from business leaders, environmental leaders, Native American leaders, local governments, mayors, chambers of commerce throughout the region that have signed on in support of this. So we feel like if we can keep growing that, we can keep this issue at the fore and get some action done. So in terms of other ways of staying informed, I would encourage you to visit songscommunity.com, our website. We post a lot of information on there, both about spent nuclear fuel, the strategic plan, and about the dismantlement of the plant. We have community engagement panel meetings every quarter, and those are done virtually now because of COVID, but would encourage you to look for when the next meetings are and tune in, because it's a great way to get a quick snapshot of things that have transpired over the last 3 months. And when we get past COVID and we begin our public walking tours again, I would encourage you to sign up for a public walking tour and come out to the plant and see what's going on. And of course, follow us on social media. We're always posting updates and information about things that are happening at the plant. So with that, I'll be happy to take any questions that anybody might have.
Great, thank you so much, John. Oh, sorry, go ahead.
Oh, sorry, John, this is Todd Priest. There were a couple of questions that were submitted online, and you've covered them, but they're worth repeating. And one I found interesting is there a way that any of the concrete or rebar could be reused for a different purpose once it's removed from the site?
A lot of the material, is going to be treated as if it is radioactive. So even very low-level Class A radioactivity goes to a special landfill. And so the Energy Solutions site in Clive, Utah, is where a lot of that material is going to be going. So not really an opportunity to recycle that.
Great. Another question was, and you covered the storage containers thoroughly, but in the event that one were to crack, what would be the outcome of that?
Yeah, so what you would have would be obviously potentially a loss, depending on what the crack would be. If it's a hairline crack, probably not very much. But what you could have would be potentially loss of some of the helium gas would come out. You might get some xenon gas from inside the spent fuel rods that could leak out, but that dissipates very quickly. So really what we're talking about, there is no, and we use this term credible scenario, where you would have radiological material leaving the site. Really, all of the materials are locked in that solid spent fuel pellet, which is encased in a welded closed fuel rod, which is zirconium alloy fuel rod. So all the nuclear material remains inside the canister. There's nothing beyond the air, the xenon gas or the helium that would come out of potentially come out of a crack. So that's the important thing. So you couldn't, some people say, well, plutonium is the most toxic material in the world and this and that, and it's really not. But that plutonium is locked inside that pellet. So you're not going to be able to extract the plutonium out of the pellet to get it out of the canister. So it's just going to stay there.
Great. And the last question I see John submitted online was, does Southern California Edison have an opinion as to where spent fuel should be stored once the federal government decides to build a storage location?
Well, what we found through the work that was done on the strategic plan is that there needs to be a federal interim storage site constructed while, and be able to be opened while a permanent federal geologic repository is constructed. Because it's very important that any community that accepts this waste needs to, it needs to be consent-based. You need to have community buy-in. It's very important because otherwise the site would likely never get finished if you had, either local community or a state or other groups, tribes who, were against that site. So building that consent is very important. And if you go back to the 2011 Blue Ribbon Commission on America's Nuclear Future, that group, that President Obama commissioned that group to do a study. Their conclusion was consent-based siting is really key to making something happen. And so if you look at examples around the world, Canada is moving along. They had a number of communities come forward that wanted to be the host of long-term spent fuel storage installations. And they looked at communities. Some of them were eliminated because of the environment or the geology or those types of things. But there are a couple that are still in the running, and those communities understand that it's can bring economic development, can bring jobs, and there's as I've sort of explained, there's very little risk in terms with spent nuclear fuel. So there could be certainly some upside for these communities in being hosts to a facility like that. But we don't in our strategic plan and what we did not choose a geographic location or anything like that. But we really outline kind of what needs to happen, and then that will be part of a process to figure out which community would like to host it. I would just like to say, once again, thank you very much for the opportunity to talk to you about what's going on at Songs. We think, it's extremely important that people understand exactly, what the risks are in terms of spent nuclear fuel, what is going on in terms of the dismantlement and how we're working to protect the environment as we go through the dismantlement. So all of those things are very key for us, and we look forward to coming back in the future with more reports of progress and hopefully some progress on spent nuclear fuel storage as well. So thank you very much.
Thank you so much, John, and your team. And it's great information today. And I personally learned a lot, and really looking forward for the more opportunity to hear more update from you guys in the near future. So thank you, and thank you all for joining us today. We're really happy that you guys got the information. And if you have any questions, please shoot us email, or you can also go to their websites. And I have already posted those sites on the chat, so you can go check them out. And once again, thank you all, and goodbye.